Okay, so thanks a lot for the opportunity to speak here with these great other speakers today. Today I would like to talk about how to choose the right metrics and why your data set matters in these respects. So let's start with an example, something that's probably known to most of us, brain tumor segmentation, like the standard application when you work in segmentation. And here you see an image of the prediction of a state-of-the-art algorithm, which gets a very high performance with the most common metric, which is used in brain tumor segmentation, the dye similarity coefficient. And if you look at the prediction and compare it to the reference, you will actually see, yeah, it looks quite good. So most tumor pixels are detected. However, the problem is that this algorithm is not as good as we think, because if you look at a different slice of this very same patient, you will see that the algorithm is really missing the small metastasis. So the new lesions, which are actually from a clinical perspective, most relevant. And the problem is that the metric behind that, the Dice coefficient, is just not able to detect these problems, because from a pixel level perspective, this algorithm would be very great. However, from like an object level perspective or a lesion level perspective, however you would like to call it, this algorithm is systematically missing like half of the lesions. So the DICE is a good example of being very bad metric to represent this clinical question and data set. And I would like to talk about a project which we call Metrics Reloaded, and it's about why we shouldn't use the most common metric. And the problem boils down to the question of when we're developing algorithms, at some point we need to decide which metric do we use to validate this. Do we use, for example, sensitivity, DICE, precision recall, whatever? But there's so many different metrics, and here you just see a fraction of them. And all of them have pros and cons. All of them have been designed for specific purposes and questions. So it's really not straightforward and trivial to find the best metric for a specific purpose. So we wanted to then know how are metrics currently selected. So is there any scheme behind that? And what we did is we looked at what challenge organizers justified their metric choice with. And here you see a few of their responses. So we very often saw these kind of replies. So things like, well, this is a widely used metric, or this is a common metric. This is the standard metric for this or that purpose. This indicates that in practice, we are often using metrics for their popularity and perhaps not for their clinical suitability, because that's just somehow what makes sense. Sometimes you cannot just have a look at each of these metrics out there to see their pros and cons. So you just have a look at papers and copy what they are doing. And if we look at some statistics, here you see the number or the frequency of metrics used across classification challenges. And that's definitely what you see in this chart here. So there are some metrics that are by far more commonly used than others, like accuracy in classification is used by so many challenges. However, accuracy is a metric that comes with very prominent pitfalls. So in the presence of class imbalance, which is very common in healthcare, we often see this pitfall. And here I wanted to illustrate this with a very simple binary classification. So you have a patient and you want to just say whether this patient is sick or healthy. We have some data set like this, so quite imbalanced. We only have 3 cases of the sick patient, of the sick class. We train an algorithm and we get an accuracy of 97%. So great score, of course. However, if we look at the algorithm, this will always say that a patient is healthy, so making it useless in practice. And this metric is just not designed to handle class imbalances. It just cannot detect it by definition. And there are other metrics, for example, balanced accuracy, which are much more suitable for these kind of problems. However, this is a pitfall that you have probably heard about. There are so many memes around these pitfalls. So I guess this is something that you can be aware of. However, still in practice, we just did a review of papers where we found that actually these metrics are still used quite often, although we have class imbalance. But if we look at the real world, we often see what we call a prevalence shift. So if you're developing your algorithm, you somehow have to make sure that the model sees both classes if we stay with binary. So if we have a disease, the algorithm needs to understand how this disease is actually provided by the data. So we try to have a balanced setting, so prevalence of something like 50%. But if we go to the real world, to the deployment data, we often have a much, much lower prevalence, like if you see in the bottom example, and we somehow have to deal with this prevalence shift. And this is why it is difficult to work with metrics like accuracy, which are concerned with class imbalance problems. And if we look at a more specific example, like very common in the past 2 years, COVID classification, assume we're really having the situation that I just described. We're training on a balanced sampling setting, and we want our algorithm to achieve specific inherent properties, so specific sensitivity and specificity to be achieved. And this could look like you see on the bottom here, we can have the confusion metric that is displayed and an accuracy and F1 score of about 80%. If we now want to use this exact algorithm with the exact inherent properties, so sensitivity and specificity, and deploy it to the real world, where we have a much lower prevalence, so not 50%, but 1%, the algorithm will score much, much lower, especially if we look at the F1 score. And the problem here is that we have a difference in prevalence. And both metrics, accuracy and F1 score, are affected and actually are based, the calculation is based on the prevalence. So changing the prevalence will affect the metric scores, which means we cannot use them to compare algorithms across data sets with different prevalences. And this is something that I, for example, didn't know beforehand. But there are metrics, for example, this one, that can compensate this fact by just using the real world prevalences and not the test set prevalences. But these are things that you just typically don't know. So, but there are other problems with metrics. So it may be about the data set that it's like, for example, class imbalance, or we have prevalence issues. But there may also be a problem with just how we phrase a problem. So often in practice, I see that you have a detection problem. So something like this example here, we have a polyp detection. We want to roughly localize the polyps, and we want to assign a class to them. So typically this is done by, for example, bounding boxes, and we're not interested in pixel level differences. But in practice, what we often see is that a segmentation metric is used to validate this. And here you see 2 examples, algorithm 1 and 2, both of them very different in what they do in terms of detecting, because algorithm 2 is detecting all 3 objects. So this would be the one that we would prefer from clinical perspective. And algorithm 1 is only detecting the large polyp, the obvious one. However, from pixel level metrics, algorithm 1 would be better. And of course, this would not be useful in clinical practice. So we should be aware of how our data sets are composed and how we face this problem. And if we now stick with object detection, it's actually more, it's not only about the metric that is used wrongly or the problem that is raised, it's also about hyperparameters of metrics. So for object detection, we have, for example, the localization or overlap threshold. So how do we define whether something is detected or not? So how much overlap do we need between my reference and my prediction to define that this is a true positive? And this threshold definitely makes a difference. In this example, for capsule colonoscopy, you see 2 algorithms, and both of them are trying to detect polyps in the same 4 images. While algorithm A is a bit more like, careful and is not detecting 2 of the polyps, algorithm B is a bit more straightforward and detects all of them, but the overlap threshold is sometimes very low. However, from the standard machine learning localization threshold, both of them would yield the exact same score from the average precision metric, because this overlap threshold would be somehow interpreted the same as not predicting at all. And actually, in our study, we found that the clinician's preference of overlap threshold is diverging quite a lot from the standard from machine learning. So it's always about your problem and not looking at what everyone else is doing. And I could talk about this the whole webinar about these problems and pitfalls, but don't want to bore you, of course. If you're interested, please feel free to check out this paper where we collected lots more of these pitfalls. But we wanted to solve this problem. And this is where we founded our Metrics Reloaded consortium with all these great experts from all over the world with different expertises. And we wanted to go for problem-aware metric recommendations. And we achieved this by performing a Delphi process where we worked together with all of these experts. We had a small group of coordinators. We worked on some proposals for the recommendations in these cases. We put it into a survey, and the expert consortium then could give feedback on that. And as you see from all these different logos and institutions, there were many different expertises. So we had machine learning experts, we had clinicians, we had biologists, prediction modelers, statisticians, and so on and so forth. So all of these different viewpoints for similar problems. So we're all working on somehow the same things, but with different use cases and different expertises, different backgrounds, but all boils together. And we wanted to combine all of these expertise to give feedback on our proposals. We integrated that feedback, we updated the recommendations, and based on this process, we could then iteratively achieve expert consensus. And our goal was here to go for problem-aware metric recommendations. So we come from what we call the driving biomedical problem, so the research question that we have. And in a second step, importantly, we're breaking this problem down into different questions. So relevant problem properties, which I will explain a bit more in a second. So we call this problem fingerprinting. This gives us like a checklist of yes or no items. And based on this, we could then decide which metrics are appropriate. So we have a pool of metric candidates. And based on your answers to the problem fingerprint, you could say, well, you should use this or that metric for this problem. And the core principle is what we call the problem fingerprint. And this is based on the pitfalls that we collected before. So we collected all of these problems that may occur with metrics. May it be related to your domain interests. So things like, am I really interested in structure boundaries, or is it okay to only focus on the center of a structure? To target structure related properties. So things related to the structures that we see in the images, dataset related properties, and algorithm output related properties. So all of these things, all of these pitfalls were converted in like a question or a property that is relevant and that we should ask for to avoid these pitfalls. And given the scope of this webinar, most importantly are these two target structure related properties and dataset related properties. And here I put them in more detail. So these are the things that mostly matter when it comes to the metric selection. So for example, do we have very small structure sizes? So if we think of the beginning, this example with brain tumors, there we really care about these tiny lesions. So this is a question that would be relevant here. Or do we have, for example, tubular shaped objects? We often see that in the surgery context where we have surgical instruments. Or things like, do we have overlapping or touching targets? Or when we come to the data set, it's more about class imbalances or prevalences, or also things like what we heard about in the last talk, uncertainties in the reference. Do we have high inter-rater variability? Or is it possible that we have spatial outliers? Or things like that are more, a bit different, like are the test cases that we have independent or not? This is important for aggregation. Do we have potentially a reference without any target structures? All of these things are possible and are breaking basically down on the pitfalls. So by collecting all of these properties, this gives us the opportunity to generalize across domains with our recommendations. So it's not important anymore whether we have, I don't know, a computed tomography image, microscopy, endoscopy, MRI, whatever kind of image. It's only important that we have somehow a classification task. And here we define classification at 4 different levels. We come from the standard classification, so image level classification, to object detection, which would be object level classification. pixel level classification, which is semantic segmentation, and the combination of object and pixel level, which is instance segmentation. And here you see the recommendation framework, which looks a bit like chaotic at the first glance, but I would like to go through it a little bit in more detail so that you understand what we are doing and how we are incorporating this fingerprint and so on. So first, we're starting with actually creating the fingerprint. We're asking all the different questions that you saw before, where you saw the examples for the data set and the target structure related properties. And you're basically saving these replies and you use that for the following steps. And one of the first questions that you see is, check the problem fingerprint category, check the problem category. So which problem do we have? Do we have an image level classification or semantic segmentation or whatever kind of classification task? And this is also what you see represented in this huge big chunk of metric selection. So you see the arrows are in different colors, which indicate which problem category you're in. And if we stick to classification, you can only focus on the blue arrows and just forget about the rest. And then it looks much easier already. And if we follow this blue path, we will see that you first end up in this box here, which says select multi-class county metric, if any, and then you have a list of candidate metrics and this plus S2 symbol, which means, okay, let's go to another decision tree, this one, which guides you through the different questions of the fingerprint. And I won't go into detail here, it's not important. It's just about, we're focusing on different questions. For example, do we have an unequal interest across classes? So if we have multiple classes, is one class more important than the others? And based on your answer, you will continue in the chart. Or do you have costs for class confusion? So is, for example, a false positive much more severe than a false negative, or other way around? And if so, do you have weights for them? Or we ask about class imbalance, and if we want to compensate this. All of this is integrated in these charts and will guide you to a decision. Or sometimes the decision is not, let's say, obvious. And we couldn't integrate every single potential use case that may exist out there. And this may bring you to a decision guide, which based on your previous replies of the fingerprint, helps you in deciding which metric is suitable for your use case. So based on your previous replies, you can see for all the suitable candidates, which are the pros and cons and which are some implications or not. For example, the balanced accuracy is a metric that is good to interpret and widely used. Perhaps that's important to you. Or perhaps it's not so great that a metric like MCC is not so easy to understand. And this is why you decide for balanced accuracy. So these decision guides help you understand your problem. And then based on your very specific use case, you can decide on which metrics is the most suitable. If we go back to the main framework, you will then just continue. You will then be asked to choose a different metric, a different kind of metric, because one important thing that we're recommending is to not only use one metric, but to use multiple, to have, on the one hand, a comprehensive picture of your performance, and on the other hand, to also compensate problems or failures of other metrics. So you then are asked to select multiple types of metrics, you follow the blue path, and then you're actually at the end here where we give some recommendations on how you actually apply these metrics, for example, how you aggregate them. But since we know that this was a bit complicated, we also provide some recommendations for specific use cases in the biomedical domain. So here you see some examples. We have more in the paper if you're interested, where we ask the community, so for which metrics would you like to see a for which data set and use cases would you like to see recommendations for metrics? And together with our expert who worked on the fingerprints for these specific examples, and we also provide the recommendations here. Another thing that we wanted to take care of is that the information is often scattered across resources. So it's really not easy to find, for example, all pitfalls of a metric. And this is why we have cheat sheets that really help you to have all the information that is relevant in one place. For example, you find the formulas, some references, relations to other metrics, pitfalls, and recommendations. Also, we found that metric implementation is not standardized. So here's an example of the, depending on which library you use, the implementation of the average precision, it completely differs and will give you very different values across different examples. And we wanted to compensate this by creating a standard implementation in the Monad framework. And here, definitely, thanks to Carol, who did most of the work, we now have a library of metrics that you can use. And importantly, you don't have to use Monai. You can use it just without using the Monai library. It's just in there as a package, but you can use it without using Monai. Yeah, and finally, we wanted to put this together into an online resource, which you can find under the link on the right, where we put all of the theory together into an online toolkit, which guides you through the whole process, so you don't have to worry about the theory and all the charts and all the fingerprint, whatever. You just go with the flow. So the system will present you with all of the different questions. It will provide you with some explanation and images and what we mean by these, so that you get just guided through the whole framework. And by doing this, you will at some point see some recommendations popping up. I think now you see the first one. And if you continue, the system will present you with the other recommendations. So, and with this, I would like to thank you for your attention and happy to take questions if you have any.